programming field. So most of the problems that we are tackling are in this area here. But I already tell you that most of the ideas that I'm presenting today, they are general, so they can be applied basically to any optimization problem. Okay, so combinatorial optimization problems, they are very important especially in industrial settings, but also in educational settings, for example. If you think about the timetabling problem in universities. So creating all the courses every year, assigning students to classes to classrooms, teachers or professors to classes, and so on. This is a huge problem, which is usually modeled as a combinatorial problem. Other examples are routing problems. For example, here you see a typical routing problem where you have a depot, where you have your trucks, for example. And then you have the customers. So these dots, they are customers. And you have to design for your routes for your trucks such that, for example, there's a whole range of different optimization criteria. For example, you want to have short routes. You want to save vehicles, maybe also. So, but the main objective is at the end saving money. Okay. Another large class of problems are scheduling problems. So this here is a Gantt chart. Usually people use Gantt charts in order to visually present solutions to scheduling problems. There you have tasks. Maybe you have to give an order to the tasks. You have to assign them to machines and so on. Okay. There are different optimization criteria like make span, for example. So you want to finish all the tasks in the shortest time possible and so on. Okay. So this is just to give you a flavor about the problems I'm talking about. When we are talking about optimization problems, we also have to talk about algorithms. Okay, so this is the other side of optimization research, algorithms for solving these problems. On one side, we have exact techniques. Okay, so these techniques, given an instance of an optimization problem, they provide an optimal solution in finite time. Okay, so here you have algorithms like dynamic programming. If you think about combinatorial problems, okay, the branch and bound algorithms and all the clever stuff that was developed in operations research. On the other side, we have approximate techniques. Okay, so sometimes it might not be possible, maybe due to the size of the problem instance that you are tackling, that you are using an exact technique, so you have to use an approximate technique. And some of the most simple approximate techniques are greedy heuristics. Okay, so there you start with an empty solution and you add one component at a time until you have a complete solution. On the other side, you have meta heuristics. Okay, so this is actually how I started in research when I did my PhD in 2004. I was starting with meta heuristics. In this class of algorithms, you have evolutionary algorithms, or some people say genetic algorithms. I think evolutionary algorithms is a more general term. You have algorithms like ant-colony optimization, so algorithms that are inspired by some natural phenomenon. Okay, like ant-colony optimization algorithms, for example, they are inspired by the shortest path finding behavior of natural ant colonies. But you have also local search-based meta-heuristics like tabu search. This is one of the oldest ones. The oldest one is probably simulated annealing. Okay, most of you probably know simulated annealing. But this is where my research is, and in the last 10 years, let's say, it was on an overlap of these two areas: exact techniques and approximate techniques. Okay, so this graphic now shows you a bit where my main research topics are. Okay, so I have basically two pillars. One of them is swarm intelligence. So in some projects, in some applications, we are working on swarm intelligence techniques. So ant-colony optimization, for example, is a meta-heuristic that falls into this class. But we are also working on swarm intelligence systems that are not necessarily for solving optimization problems, okay, maybe control problems. And on the other side, I have this pillar on hybrid meta-heuristics. Okay, so this is where we have algorithms that are from the overlap of that result from the combination of exact and meta-heuristic techniques. So, but before I start with this part, actually, I want to give you a short flavor of the other one. Okay, these are just 3-4 slides on this, such that you get an idea what our research topics there are. Okay, so what is swarm intelligence? In one sentence, we could say that it's an AI or artificial intelligence discipline whose goal is designing intelligent multi-agent systems by taking inspiration from the collective behavior. This is very important, of animal societies. Okay, so examples are ant colonies, flocks of birds, fish schools. Here you see 3 examples of results of a swarm intelligence system. Okay, so here you have a termite mound. No termites, these small insects. They build incredibly large nests or mounds. So this one might be maybe 5 meters high. Okay, so they have a complex internal structure. So, for example, there are chambers in there that have the same temperature all over the year, no matter what the outside temperature is. Okay, and the point is that none of these termites actually knows how to build that. Okay, so this is a result from a set of simple local rules. Okay, so the termite might find a specific situation and might react according to a simple rule. Okay. The second example I have here is these geese flying in V shape. This is also the result of following simple local rules. And these rules, they have evolved because when they fly in this way, they can save energy. Okay. So there will not always be the same bird flying in the front position, because this would be actually very bad for this bird. So they are changing positions during flight. Okay, but as a whole, as a flock, they can save energy. Actually, I know from military experiments where they let fighter airplanes fly in this V formation, and I think they could save up to 20% of fuel globally. Okay, so the third example is a fish school. Okay, for sure you have seen it live in the best case, or you have seen videos or films about fish schools. So they all seem to be moving or reacting at the same time, moving to the same direction. Is very nice to look at. This is also the result of following simple local rules, and this has evolved partly as a protection against predators. Okay, so when predators see a fish school moving in this way, they have difficulties picking a single fish, and then at the end, sometimes they don't catch any fish. Okay, so these are examples. We can see, look at it also from a more technical perspective. Okay, so what are the properties of swarm intelligence systems in nature, and also from a technical point of view? So they consist of a set of simple entities. Okay, they are completely distributed, so there's no global control. Actually, until the 50s, biologists still thought that the queen, for example, in a beehive, would know or would give orders when to execute certain tasks. Okay, so she would have some control, but this turned out to be wrong. Okay, actually, the behavior of beehives, for example, they are completely self-organized, and this self-organization is a result of different ways of communication. Okay, so on one side you have direct communication, for example, by visual or chemical contact. So when an ant, for example, when an ant finds a prey that is too heavy, too large to be carried by the single ant, she would recruit other ants helping her to carry this object, okay, or cutting it into pieces. But the important way of communication for swarm intelligence is the indirect communication. Okay, this was labeled stigmergy by a French biologist called Grasset in 1959. And this graphic here shows basically how it works. So E means environment, R means response. Okay, response of the colony, for example. So when the environment is in a specific state, this triggers a response of the colony, and then this in turn changes the environment, which in turn again triggers a different response, and so on, until the environment at the end is in a final state for this task. Okay, for example, building a nest. So complex tasks can be accomplished in cooperation. So this is the important term here, in cooperation. So just to give you an idea of what we are working on in this area and what we have been working on. So at the moment, if you look at the meta-heuristic, concerning the meta-heuristic uncolony optimization applied to combinatorial optimization problems, we are trying to add actually negative learning. So if you think about learning algorithms in the field of meta-heuristics, at least, they are basically all based on positive learning. So learning from positive examples, from good solutions, okay? In nature, on the other side, you find also examples of negative learning. So for example, antipheromones, or no entry markers, for example. And they often are very beneficial for the system to stabilize. And this is what we try to add. Okay, together with the PhD student, since about 1 year, we are working on this. The other two projects are already 3-4 years old. So, for example, in one of these projects, we looked at distributed optimization. So, for example, graph coloring from a distributed point of view. Okay, so this means you don't know graph that you want to color. Everything is seen from the viewpoint of the nodes, okay, of the node. Each node of the graph just knows its neighbors, for example, okay? And then you have to find a distributed algorithm that works on the basis of the nodes of the graph in order to color the graph. And in order to do that, we used a self-desynchronization behavior that you find in Japanese tree frogs. Okay, it's very, very interesting behavior. The male Japanese tree frogs, they are calling for the females, okay, and the females, they listen at the calls and decide for a male. However, when two male frogs would croak at the same time, the female could not listen to the croaks, and could not distinguish, or would not know where to go, okay. So it couldn't determine the direction. So these male frogs, they have a distributed way of desynchronization, and this is what we used here. And the last example I want to mention is duty cycling and sensor networks. So when you have sensor networks, you have small devices usually which are equipped with batteries, and so you have to save energy basically. So they are depending on the task that you want to solve with the sensor network, they are periodically switched off. Okay, and this can be also done in a distributed way. What we have shown with a system which is based on synchronization that you find in ant colonies, the verb synchronization. So sometimes, some moments in time, nearly all the ants in the colony would be inactive or sleeping, if you want, and in other moments of time they would be nearly all active. Okay, so this is in the way of the mechanism that they use for achieving that. We use this mechanism for duty cycling. Okay, but now I want to switch to the other part, and if you want to know more about these topics, I would invite you to visit my webpage. Okay, so now let's talk about hybrid meta-heuristics. first of all, what is a hybrid meta-heuristic? There we run into the first problem. A precise definition is not really possible, okay, or desirable even. We can give a possible characterization, okay, so we could say is a technique that results from the combination of a meta-heuristic with any other technique for optimization, not necessarily with exact techniques. Before I said exact techniques, because we are looking basically on exact techniques, but you can get a hybrid by combining a meta-heuristic with anything. So other meta-heuristics, for example, branch and bound algorithms, dynamic programming, and so on, okay? What is their reason of being? So why did they come up? Why did people come up with hybrid meta-heuristics? Why did they get the idea of combining different optimization algorithms? And one answer, I'm sure there are more than one, but one answer to this question is the size of problem instances. Okay, so the problems that are solved in industry, they're growing, they're always growing. Okay, so the size of the problems they want to solve nowadays has nothing to do with the size of problems they wanted to solve 20 years ago. And what happens usually is that exact techniques, they're working very well for certain problem sizes, problem instance sizes, until you reach often a phase transition where they suddenly start to fail. Okay, and then you have to resort to approximate techniques like meta-heuristics. But then when the problem size grows even more, sometimes even meta-heuristics are lost in the large search spaces, okay? So this is one of the reasons why people came up with hybrids, so combining different types of algorithms, exact ones with approximate techniques, for example, in order to exploit the synergies that you get when you combine, that you might get when you combine different types of algorithms. Okay, a little bit about the history. So for a long time, the different communities in optimization, they coexisted quite isolated. Okay, so even if you look at the meta-heuristics field, the people that were working on evolutionary algorithms at the beginning, they didn't look what the people in simulated annealing or tabu search were doing. Okay. There are several reasons. One of them is surely that you are at the beginning, you are very focused on your own technique and you want to sell it also. Okay. But then at some point, also because of the growing problem instance sizes, and this happened maybe about 15 years ago, people looked at hybrids. Okay, and then you see that also on the appearance of specialized conferences and workshops. Okay, so the first one I think was from '99. So the first time CPAIOR was held was in '99. In 2004, we initiated I, together with some colleagues, we initiated a workshop series on hybrid meta-heuristics. And in 2006 was held for the first time the math heuristics workshop. Okay, and since then I would say the term hybrid meta-heuristic or math heuristic sometimes, if you only look at combinations of meta-heuristics with mathematical programming techniques, identifies really a separate line of research. Okay, so my plan is as follows. I'm going to show you now 3 examples in a rather summarized way. Okay, and then I'm going into an example of a hybrid technique that we developed in our own group, and I will go more in detail into this example. Okay, just have a look how much time I have. Okay. So the first example I want to present are decoder-based approaches. Okay, so the general idea is that we represent feasible solutions to our problem that we want to solve in an indirect way. Okay, so in a way that requires a decoder in order to translate such a solution that is represented in an indirect way into an actual solution of the problem. Okay, so in many cases, this transforms a complex search space into one that is much easier to handle, for example, constraint-wise. Okay, because it encapsulates problem complexity into the decoder. Okay, so it puts complexity of the problem into the decoder that you don't have to look at when you run your meta-heuristic, for example. Okay, this is very beneficial sometimes. This is, in general, these decoder-based approaches, they are very well known from the field of evolutionary algorithms. Okay, for example, the biased random key genetic algorithm, if you know this one, solutions in biased random key genetic algorithms are always represented by real valued vectors, okay, where each position has a value between 0 and 1, no matter what the problem is. Later, you have to design a decoder that translates such a random key into a solution, into the actual solution to the problem. Okay. But of course, these decoder-based approaches, they also use clever, exact techniques, let's say, as decoders. And I want to show you an example of that kind. Okay, so this is the paper here from which I took this example. It's already quite old, but I took it because it's very intuitive. Okay, so there are decoder-based approaches published every year, but this one is quite intuitive. And this approach is for a problem known as the generalized minimum spanning tree problem. Okay, so you have given a graph. All the dots here are nodes of the graph. Small dots, okay. This graph is completely connected and you have a distance between each pair of nodes. And in addition, you have clusters, okay. So all the nodes of this graph are clustered in this example, into 5 different clusters. These are these gray areas here. These are the clusters, okay. And a feasible solution to the problem is a tree that is a subgraph of the input graph that contains exactly one node from each cluster, okay? And the objective function value is, you obtain the objective function value by summing the distances on the edges of this tree, okay? You want to minimize. Okay, here you see already you have basically two levels of decision, okay? Which nodes do you choose in each cluster? And how do you connect that then into the best tree possible? Okay, so the researchers from this paper, they have 2 options. Okay, the first one is define a feasible solution as a set of nodes which contains exactly one node from each cluster. Okay, so we represent feasible solutions like that. The decoder then applies, for example, Prim's algorithm or the Kruskal algorithm to get me the best tree that I can define on these 5, in this example, on these 5 nodes. Okay, so in each solution evaluation, when I use the decoder, I have to run Prim's algorithm or Kruskal's algorithm. They also defined a second option. Okay, so define a feasible solution as a spanning tree of the clusters. Okay, so I can look at the higher level graph where I have 5 nodes. These are the clusters, and solutions are all the spanning trees that I can generate with these 5 clusters. Okay, so my meta heuristic in this scenario looks at all searches in the search space of all spanning trees of these 5 clusters. Okay, and then these researchers used a clever dynamic programming algorithm. Okay, when they have a spanning tree like this, they use a dynamic programming algorithm that tells them exactly which node to choose from each cluster in order to get the best possible tree for this spanning tree. Okay. And then you need you can run basically any meta heuristic on that. Okay, so you can use an evolutionary algorithm, for example. You can use a variable neighborhood search or whatever. Okay. So the second example that I want to explain is on multi-level frameworks. I want to go rather fast over that because I'm speaking already for 30 minutes. So The general idea is first you iteratively coarsen the original problem instance, then you find a solution to the coarsest level, to the smallest level, and then you iteratively refine the solution at each level. Okay, so let's have a look at this graphic. This explains how it is done. Okay, so this is the original problem instance here, and you could run a meta heuristic on this problem instance in order to get a solution. Okay, but instead of doing that, we are contracting somehow, coarsen this problem instance. We make it smaller, okay? And this is usually done by joining elements somehow, okay? If you think about a graph, you could join neighboring nodes, for example, okay? So you make the problem iteratively smaller by coarsening it, and then you run your meta heuristic on the most coarse level. This gives you a solution. And then you expand this solution to be a solution for the next level. And then you can run your meta heuristic again to improve this solution. And you go on like this, okay? You expand it, you expand the best solution that you get for this level to be a solution for this level. Then you run your meta heuristic in order to improve it and so on, okay? And at the end, you have a solution to your original problem. So the first paper on this was from 2004, I think. But there's still, I think it's a very powerful framework, especially, of course, when you think about problems in graphs. And you see this paper is, for example, from 2020. This year, this paper is from last year. So every year there are papers on that make use of multi-level techniques. Okay, the third example I want to quickly explain is on combinations of meta-heuristics with machine learning. Okay, so machine learning, as you know, is a branch of artificial intelligence where we develop algorithms with the ability to learn without being explicitly programmed. Okay, you also, I'm sure you have heard about deep learning. So this is part of machine learning where we deal with multi-layer neural networks, which were not really applicable until, let's say, 9 to 10 years ago, when NVIDIA developed the GPUs that could be used for training them, okay? And when they suddenly got very, very, very powerful for areas like computer vision, for example, okay? So there are different architectures. There are many architectures nowadays. In fact, I just put two here as an example. So you can have recurrent neural networks, for example, convolutional neural networks, graph neural networks, and so on. Okay. So actually, there's a nice paper which was published this year by Bengio, Lodi, and Provost. And this paper gives the first survey, let's say, on how to use machine learning and often deep learning for combinatorial optimization. Okay, so I really recommend, if you want to know more about this, to look into this paper. What they say is that there are at least two ways for improving meta-heuristics or algorithms for combinatorial optimization. The first one is generate a fast approximation for heavy computational tasks. Okay, so for example, you can imagine a problem. It takes ages to evaluate one solution. Okay, in these cases, it's often it's impossible to run a meta-heuristic because you have to evaluate many solutions. Okay, so if you can approximate such an objective function with a neural network, for example, then this is much faster. Okay. For me personally, the second option or possibility is much more interesting. Learning missing expert knowledge. Okay, for example, greedy functions, because sometimes we are faced with a problem where we don't have, and we cannot even think of a good greedy function, for example, or a good neighborhood function. Okay, and I just want to tell you about this paper here, which is called Learning Combinatorial Optimization Algorithms over Graphs. So they look at different graph-based combinatorial problems like minimum vertex cover, maximum cut, traveling salesman problem, okay? And they want to learn basically a system that is a greedy algorithm, okay, for these problems. So they learn a system that, given an input graph, given a partial solution, and giving the options of how to extend this partial solution, the system tells you which option to choose. Okay, this is basically what a greedy function does, right? They used a deep learning architecture called structure-to-vec. They used a type of Q learning, and they learned greedy policies in this way that outperform classical greedy algorithms for these three problems. Okay, and the good thing is that they even generalize to different problem instance sizes. Okay, so you can learn, for example, you can train the system with, let's say, graphs of size up to 100, and then you can apply it to graphs of size 1000, and it generalizes. Okay. Actually, we are also working with a PhD student on a system like that, okay, for a problem called capacitated minimum dominating set. Okay, but I don't think I will go into this now. I will go to my main example. So I will jump over 2 slides and give you this main example of one branch of our work in the last 4 years. Okay, so algorithms based on problem instance reduction. Okay, the main idea here is to apply an exact technique to sub-instances of the original problem instance. Okay, I will explain these algorithms, which are very simple, for their application to subset selection problems. Okay, this is just that I don't have to go so deep into technicalities. Okay, but keep in mind that these algorithms can be applied to any combinatorial problem. Okay, just that here now I explain them for subset selection problems. A subset selection problem is a triple like this, where C is a finite set of n items. Okay, F is a function that tells me for each subset of C if it's a valid or an invalid solution. Okay, that we can call the set of all feasible solutions by X. And then we have an objective function, okay, that gives us for each feasible solution an objective function value. Okay, so actually many combinatorial optimization problems can be expressed as subset selection problems. One example is the TSP. Okay, you can see a TSP solution as a subset of the edges of an input graph, and you're already there. Okay. So if you think about algorithms in which you want to apply exact techniques to sub-instances, I would say the standard algorithm nowadays, the standard hybrid algorithm, is large neighborhood search. Okay, just to explain what it is, it's a neighborhood search method. Okay, so you have a solution, you generate a neighborhood, and you move in each step to one of the neighbors of the current solution. Okay. So when I use neighborhoods that are small, I have the advantage, small, this means every solution has only a few neighbors, okay? And the advantage is that it's fast to find an improving neighbor because I just have to look at very few neighboring solutions. The disadvantage is that the average quality of the local minima is low, okay? When I use large neighborhoods, the advantage is that the average quality of the local minima is rather high, because every solution has many neighbors. But the disadvantage is that finding such an improving neighbor might itself be an NP-hard problem. Okay, so there we might use exact techniques for searching large neighborhoods. Okay, and this is a solution for a destruction-based large neighborhood search that is often used in the first attempt, let's say. Okay, so you generate in some way an initial solution, for example, by using a greedy heuristic. Okay, you have your initial solution S. Then in each iteration of the algorithm, you first destroy the solution partially. This gives you a partial solution. Then you apply your exact solver to find the best solution that contains this partial solution. Okay, so you restrict your exact solver to this part of the search space, where you only have solutions that contain S partial. And then you choose between S and SILP. If you use an ILP solver, I should have called this differently. You choose the solution for the next iteration, okay? Because you go back to here. Okay, so you do these 3 steps over and over again. As an alternative, in a PhD of one of my students 4 years ago, we developed an algorithm that we call construct, merge, solve, and adapt. Okay, so it was first published in this paper here in Computers and Operations Research in 2016. And the results that I want to show you later, or the comparison, is from a paper from this year, which was just accepted, okay, in Edge. So this is how construct, merge, solve, and adapt works for subset selection problems. Okay, let's go slowly through this slide. Okay, so C, remember, C is the complete set of items, and C prime, any subset C prime is a sub-instance. Okay, so this is a reduction of the item set. Okay. Each item has an age, okay, an age value which is initialized to 0. Then in each iteration, we do the following 4 steps, okay? First, we probabilistically, for example, by using a greedy heuristic in a probabilistic way, we probabilistically generate a number of solutions, okay? And let's C hat be the set of items used in these solutions. Then we add C hat to my sub-instance, okay, which is initially empty actually. And then we apply our exact solver to give me the best solution that I can generate by exclusively looking at items from C prime. Okay, so this is a subspace of the original search space. Then we increment the age of all items in C prime in the sub-instance, okay. And afterwards, we set the age of all items that are in the best solution to the sub-instance to 0. Okay, so this is like equality. If your age gets back to 0, this means you can stay longer in the sub-instance. If your age always grows because you are never in the best solution to the sub-instance, then here in the last step of the algorithm, you will be kicked out from the sub-instance actually. So remove all items from C prime whose age is equal to H max. Okay. So you see that large neighborhood search and also this one, they're rather simple and general algorithms. Okay. I want to show you some examples, some results for the comparison of these two in the context of a problem which is called multidimensional knapsack. I'm sure most of you know this problem. Okay, it's very easy to explain. You have a set of items, n items. We have k resources, m resources. Each resource has a maximum quantity, ck, or the capacity. Each item I requires from each resource k, if chosen for the solution, a certain quantity rik, okay? And each item has a profit, pi. Okay, so valid solutions are subsets of the complete set of items, and if they fulfill these constraints here, okay? So this is our solution. So I am summing over the resource requirements of all the items in my solution for each resource, and I have a look if this sum of the resource requirements is below or at least at most the capacity for this resource, okay? So this has to be fulfilled. And objective function is simply I'm summing the profits of all the items that I have in my solution. Okay. So what we need in order to apply these two algorithms, LNS and CMSA, to this problem is a greedy heuristic. Okay. Due to time constraints, I will not go into this. You need a greedy heuristic, so we have it here. It's very simple, and we are using as an exact solver. We are using CPLEX in this case. CPLEX is a system for solving integer linear programs. Okay, and this is the integer linear program for the multidimensional knapsack problem. okay? For the application to sub-instances in LNS, we simply fix all the items that are in my partial solution to 1, okay? The value of all these variables, I should set them to 1. And in CMSA, I replace, in this model here, the complete set of items with the sub-instance, okay? With the reduced set of items. Okay, so we generated a whole range of different instances, and which depend especially on a parameter alpha. So if alpha is close, this is a parameter between 0 and 1. Okay, so if alpha is close to 0, I get instances where solutions are very small. Okay, so solutions contain only few items, and when alpha is close to 1, I generate instances where solutions are very large. Okay, and that we generated solutions over the whole range, and we tuned both algorithms, the parameters separately for each value of alpha. Okay, and this is what we get. Okay, so in these graphics, on the x-axis here, we see instances from different alpha values. Okay, so these instances are instances with very small solutions. And at the end here, these are instances with very large solutions, okay? And for each alpha value here, we generated 100 instances randomly and run our algorithms. Now, boxes, what they show is the following. So if this box is above the 0 line here, then CMSA is better than LNS. And if this box is below, LNS is better than CMSA, okay? And now you see that for item sizes 500 and 1,000, for example, basically there's no difference between the algorithms, okay? On average, they perform the same, okay? Even though for some instances, one is a bit better, and for others, but in turn, for others is a bit worse, okay? Now, if we go to larger problem instances, so like with 5,000 items and with 10,000 items, we start to see something curious. We see that CMSA suddenly improves over LNS for instances where solutions are rather small. Okay, so our hypothesis is that this is because CMSA allows to do bigger jumps in the search space. Okay. In LNS, in this destruction-based LNS, you are tied to at least maintaining part of the solution when you move to the next solution, okay? Because you just partially destruct the solution at each iteration, okay? And this doesn't allow you to do as jumps as large as in CMSA, okay? I just want to go quickly also into this visual way of comparing algorithms. Okay, this was the first time actually that we presented this way of visually comparing algorithms. Okay, I just want to explain you on this example graphic what these graphics show. So the yellow dots here, they are starting points for algorithms. Okay, they are solutions, and the yellow dots are starting points. Blue dots are only visited by LNS. And these orange dots, they are only visited by CMSA, okay? If a solution is visited by both algorithms, then it's in green. The best solution found is in red, okay? And these dark gray solutions are other endpoints of trajectories, okay? So this gives us a network that we can analyze visually, but also by means of measures, okay? So in this graphic, actually, you see 3 runs of LNS. They all start from the same initial solution. This is because we are using a greedy heuristic for generating the starting solutions, okay? And CMSA starts from different places because we are using a probabilistic greedy heuristic, okay, for generating the solutions at each iteration, okay? So now let's have a look at the real result graphics, okay? So this is for 10,000 items and for instances with very small solutions, okay? So what can we see? This is LNS here, okay? We see that all the 10 runs of LNS actually, there's no overlap and they end up in different solutions. So all the ending solutions of trajectories are different. And while the CMSA runs, there seem to be attractors in the search space, these bigger nodes here, where many runs of CMSA end up. And actually, there's also the best solution found is one step away from one of these attractors. Okay, so only visually exploring these graphics tells us already that for this type of instances, CMSA clearly works better. Okay. Now, if we go to instances of medium tightness, okay, so this would be for an alpha of 0.5. This would be for solutions of medium size. We see that now there is some overlap of the algorithm between the algorithms. Okay, there's some attractor in the search space that attracts some runs of both algorithms. Okay, the best solution actually was found here by LNS. It seemingly doesn't have anything to do with this attractor, but the distance of the nodes here doesn't say anything about distance in the search space. Okay, so it might well be that this solution is actually also close to this attractor. Okay, just that none of these runs that went into this attractor here ended up here. Okay. What we also see is that for CMSA, there are 3 runs that go astray somehow, that have nothing to do with the rest. Okay. When we go now to the instances with the largest solutions, this is more extreme even. Okay. Here we see that CMSA has 5 runs that, or 5 that have nothing to do with the other runs. Okay. And again, there's an attractor region where both algorithms basically end up in most of the runs. Okay, so we believe that this tool is actually quite nice for understanding algorithm behavior. And at the moment, we have a paper under submission about this tool, okay, where we apply this tool for combinatorial problems, but also for function optimization. Okay, and we give examples of how to use it. Once this paper is accepted, we also will make this tool available. Okay, so everyone can use it. I think I will come to an end. So this is just a comparison to the state of the art, where we show that actually this was a review of this paper asked for a comparison to the state of the art. Actually, we never thought about it because our aim was different. But when we did it, we could show that actually this is our algorithms, even though they are very simple, they are on level with state of the art heuristic optimizers for the multi-dimensional knapsack problem. Okay, just to conclude, hybrid meta-heuristics. In my title, I said that most of the algorithms are hybrid nowadays. This might be a bit exaggerated. Okay, so many of them, and every time more of them are hybrids, I think. The reason of being is that especially the size of the growing size of the problem instances in real life, they profit. The advantage is that they profit from synergies. When you combine different algorithms from different areas, you get often synergies if you combine them in the correct way. Okay, and possible research directions. Well, let me start with the second one here. So, in my view, the combination with machine learning is very promising. You see, I think if you look at the curve of papers on this topic, combining or using machine learning somehow for optimization algorithms, you see an exponential growth. Every year you see many more than the year before. So this is especially promising area, I would say, but also you can work on existing approaches, so contributing to a deep understanding or improving these approaches. Okay, just want to say a quick thank you to some of the colleagues involved in this work. So Pedro, for example, Pedro Pinacho, he's now an associate professor in Chile, in Concepcion. He was one of my PhD students, and he started the work on CMSA. I'm working a lot with my good colleague and friend Günther Reidel from Vienna. If you are in operations research, probably you have heard about heard his name. I'm lately also working with Gabriela Ochoa from the UK. She's especially working on visualization aspects. Okay, so she prepared this tool for visualizing algorithm behavior. Okay, just some literature at the end. I would recommend this first book here. This is an edited book, but it's very well planned. Okay, this is already the third edition, the Handbook of Meta-Heuristics. We also have a chapter in there on hybrids. And together with my colleague Günther Reidel, we published a book in 2016, a written book dedicated to hybrid meta-heuristics. So if you want to know more about up until 2016, it's already 4 years old, which is quite old already in our field. But anyway, this gives you a lot of background knowledge. Okay, so thank you very much for your attention.
Thank you, Christian. It was very interesting talk. Now it's time for questions. If someone of participants have any questions. Maria, do you see some questions?
If not, you have to ask Stefka.
Christian.
Okay, guys, if you have questions, you have to raise your hand. The raise your hand is on the bottom right corner, or you can also use the chat feature and type your question. I'm gonna be checking if there are any hands that have been raised. So far, I don't see anybody raising the hand. And let me check the chat. I don't see anything in the chat for the time being. So, Stefka, do you have any questions?
Maybe one comment at the beginning. Christian say about negative experience of the algorithm, and maybe 10 years ago with my colleague.